The primary duty of an industrial hygienist is to ensure that the concentrations of environmental contaminants in the air are at the lowest and safest levels possible. This is accomplished through implementing preventive measures in hazardous areas and by providing air monitoring to confirm that the levels meet both government and institutional regulations. The various environmental factors or stresses that can cause sickness, impaired health, or significant discomfort in workers can be classified as chemical, physical, biological, or ergonomic. Chemical hazards arise from excessive airborne concentrations of mists, vapors, gases, or solids in the form of dusts or fumes. Additionally, some materials may irritate the skin or be absorbed through the skin. Physical hazards include excessive levels of non-ionizing radiation, such as radio or microwave transmission and similar types of non-ionizing radiation. Ionizing radiation is more closely associated with nuclear radiation. Ergonomic hazards include improperly designed tools, work areas, or work procedures, improper lifting or reaching, poor visual conditions, or repeated motions in an awkward position can result in accidents or illnesses in the occupational environment. Designing the tools and the job to fit the worker is helping to prevent ergonomic injuries. Biological hazards are any living organism or its properties that can cause an adverse response in humans. Primarily in healthcare, biological hazards can be found almost anywhere after disasters and similar situations. The majority of occupational health hazards arise from inhaling chemical agents in the form of vapors, gases, dusts, fumes, and mists, or by skin contact with these materials. The degree of risk in handling or given substance depends on the magnitude and duration of exposure. Each chemical produced by a chemical manufacturer must have a Material Safety Data Sheet, MSDS. The MSDS is a summary of the important health, safety, and toxicological information on the chemical or the mixture ingredients. Other stipulations of the Hazard Communication Standard require that all containers of hazardous substances in the workplace be labeled with appropriate warning and identification labels. Solvent vapors enter the body mainly by inhalation, although some skin absorption can occur. The vapors are absorbed from the lungs into the blood and are distributed mainly to tissues with a high content of fat and lipids, such as the central nervous system, liver, and bone marrow. Dangerous materials are chemicals that may, under specific circumstances, cause injury to persons or damage to property because of reactivity, instability, spontaneous decomposition, flammability, or volatility.
This video focuses on 4 major accidents investigated by the CSB, accidents that demonstrate what happens when reactions run out of control, resulting in fires, explosions, and toxic releases that cause death, injury, and environmental damage.
Such an accident unfolded on the morning of January 31, 2006, when a vapor cloud exploded at the Synthron acrylic polymer manufacturing plant in Morganton, North Carolina. The blast killed 1 worker and injured 14 others. It destroyed the facility and damaged nearby structures. Synthron manufactured acrylic polymer coating additives in batches using a 1,500-gallon reactor located inside a production building. The company had produced the polymers for years without serious incident, typically using a 2-step process. In the first step, operators would partially fill the reactor with acrylic monomer and solvent, warm the vessel with steam, and then initiate and run the reaction for up to several hours. Later, in a second step, operators would gradually pump in the remaining acrylic monomer and continue the reaction until the vessel was nearly full of product. Both steps of the reaction generated heat, causing the solvent to boil. An overhead heat exchanger condensed the hot solvent vapors and sent cooler liquid back into the reactor, keeping the temperature and the reaction under control. Shortly before the accident, Synthron received an order for an acrylic product that was 12% larger than the standard batch size. Rather than fulfilling the order by making 2 smaller batches, managers decided to make a single, larger batch and to add all of the extra acrylic monomer during the first step of the process. But this was a critical mistake. Adding the extra monomer all at once more than doubled the heat released by the reaction. The heat exchanger could not condense the vapor quickly enough, and the temperature and pressure inside the vessel began to rise uncontrollably in a runaway reaction. The pressure caused the gasket on a hatch to fail, releasing flammable solvent vapor into the building. Employees heard a loud hissing sound, saw the escaping vapor, and fled the building. 4 workers gathered outside a doorway, where they were joined by the plant superintendent and the plant manager. One of the operators went back inside the building in an attempt to send emergency cooling water to the reactor. But it was too late. The operator returned to his companions outside. Seconds later, the solvent vapor in the building exploded. A worker who had remained inside the lower level of the plant was fatally burned, and 14 others were injured. The building was destroyed.
In 2002, the CSB completed a comprehensive study of reactive chemical hazards, issuing key safety recommendations to OSHA and the EPA, as well as trade and industry groups. A number of the recommendations have yet to be adopted. The report identified 167 serious accidents involving uncontrolled chemical reactions in the United States over 2 decades, causing 108 deaths and hundreds of millions of dollars in property damage. More than half involve substances not covered under current federal process safety regulations. Between 2002 and 2007, the CSB investigated 10 additional serious reactive accidents and identified many others that caused deaths, injuries, evacuations, or property damage.
On March 13, 2001, 3 maintenance workers at the BP Amoco Polymers plant were killed while they were preparing to clean out a tank that held waste plastic. BP Amoco made high-performance nylon by pumping raw materials through a heated reactor and then using an extruder to form the hot plastic into solid pellets. During the first 50 minutes of startup, plastic considered to be unusable was diverted away from the extruder to a 750-gallon waste tank. Steam and gases escaped through a vent in the waste tank, preventing any accumulation of pressure inside. The contents of the tank were allowed to cool down over a period of hours. Workers then opened the cover to remove the waste plastic. On the afternoon before the accident, operators began to start up the process. But there was a mechanical failure in the extruder. While the operators tried unsuccessfully to fix the extruder, the hot plastic continued flowing into the waste tank for an unusually long time. Supervisors eventually aborted the startup, but by then the waste tank had already overfilled with molten plastic. The excess plastic clogged the vent line and the emergency pressure relief line. With the lines and pressure gauge now sealed off, workers would have no reliable way of determining whether the tank was under pressure. As the outside of the waste tank gradually cooled, a hard plastic layer several inches thick formed around the inside surface of the tank. But closer to the center, the plastic still remained hot and molten. Unknown to workers, a slow decomposition reaction was occurring inside the molten plastic. Over a period of hours, the hot plastic molecules were breaking down, forming gas bubbles and causing a dangerous buildup of pressure. Just after 2 a.m., 12 hours after the startup attempt, 3 night shift workers approached the waste tank to clean it out. The workers began to unbolt the cover of the tank. After they had removed half the bolts, the extreme pressure blew the 1,750-pound cover off the tank with explosive force and ejected hot plastic over a wide area. The waste tank recoiled backward, breaking hot oil pipes and creating a vapor cloud which ignited 6 minutes later. 2 of the maintenance workers were killed instantly when the tank cover blew off. The 3rd was pronounced dead on arrival at a hospital.
The CSB's 2002 study found that over 90% of serious reactive chemical accidents involve hazards that have already been described in the publicly available literature. The board recommended that, to better understand reactive hazards in their processes, companies should consult multiple sources of information and conduct specialized testing if necessary. Collecting adequate safety information and data is especially important when scaling up a reactive process.
On April 12, 2004, the MFG chemical plant in Dalton, Georgia, experienced a runaway chemical reaction. It caused the release of highly toxic vapors into a residential community. MFG was contracted to manufacture 35,000 pounds of a plastics additive called triallocyanurate, or TAC. The company produced 3 trial batches of TAC by reacting aloe alcohol and cyanuric chloride inside a small 30-gallon test reactor. In the first 2 tests, operators controlled the exothermic or heat-producing reaction by adding one of the raw materials in small portions. In the third test, all of the chemicals and a catalyst were combined in the test reactor at one time, which was the procedure that MFG later decided to use when scaling up to full production. This third test produced significant heat, but the water cooling jacket around the small vessel was able to keep the temperature low and control the reaction. However, MFG did not realize that compared to the small test reactor, it would be far more difficult to control the temperature in the 4,000-gallon production vessel. The surface area to volume ratio was much lower in the production vessel than in the test reactor. Starting the production process for the first time, operators loaded the large vessel with all of the cyanuric chloride powder and the catalyst. They then added all of the aloe alcohol and began mixing the chemicals. To control the temperature, MFG had rented a portable chiller and connected it to the cooling jacket on the vessel. But as soon as all of the raw materials were combined, the reaction began producing heat faster than the cooling system could remove it. The temperature increased uncontrollably, and with all of the raw materials already in the vessel, nothing could be done to control the reaction. The pressure inside the reactor climbed rapidly as the mixture heated. Suddenly, a gasket blew out, releasing toxic aloe alcohol and aloe chloride vapors into the atmosphere. About 10 seconds later, the emergency pressure relief rupture disc burst open, releasing more vapor. Unable to slow the reaction or contain the release, the operators were forced to evacuate to a safe location upwind. The toxic vapors quickly spread into the residential neighborhood east of the facility. Authorities ordered the evacuation of more than 200 families, but the town had not trained or equipped its emergency responders for such an accident. 154 people had to be decontaminated, including 15 police and ambulance personnel.
On October 13, 2002, an explosion tore apart a 145-foot distillation tower at the First Chemical Corporation in Pascagoula. 3 distillation towers at the facility separated and purified mononitrotoluene, or MNT, which is used in the manufacture of dyes and agricultural chemicals. The entire facility was shut down for routine maintenance. Plant operators decided to leave 1,200 gallons of MNT inside one tower during the shutdown. This would be safe at normal temperatures where MNT is stable. The heating was shut down on the 2 reboilers by closing the steam supply valves. But unknown to operators, these valves were corroded and worn. Steam leaked into both reboilers over a number of days, heating up the MNT, causing it to break down and become unstable. On the morning of the accident, the temperature inside the tower reached 450 degrees Fahrenheit. A dangerous runaway reaction began, rapidly forming gas and suddenly building up pressure inside the tower. The tower began to rumble, and employees saw material venting quickly from a breach high in the tower. A short time later, the tower ruptured. The violent explosion propelled the top 35 feet of the tower well beyond the plant site. Another piece of the tower sailed 500 feet and hit a storage tank of MNT, setting it ablaze. A 6-ton piece of the tower sidewall flew 1,100 feet and came to rest just 50 feet from a 250,000-barrel crude oil storage tank. A piece of shrapnel nearly hit a 500,000-pound tank of toxic anhydrous ammonia. Metal packing covered in flaming chemical residue ejected from the tower and rained down across the facility and neighboring plants. the explosion knocked down 3 operators who had taken shelter just inside the control room door.
Explosives are substances, mixtures, or compounds capable of entering into a combustion reaction so rapidly and violently as to cause an explosion. Corrosives are capable of destroying living tissue and have a destructive effect on other substances, particularly on combustible materials. This effect can result in a fire or explosion. Flammable liquids are liquids with a flash point of 100 degrees Fahrenheit, 38 degrees centigrade, or less, although those with higher flash points can be both combustible and dangerous. We'll discuss flash points shortly.
The U.S. Chemical Safety Board issued a safety bulletin in January of 2006, warning acetylene producers of the dangers of allowing the violently explosive gas to accumulate in enclosed spaces. The bulletin cautions acetylene producers to maintain up-to-date procedures and checklists, train their personnel, and ensure that acetylene can only vent to safe locations. The CSB Safety Bulletin followed an investigation into the January 25, 2005 explosion at Acetylene Services Company, or ASCO, that killed 3 workers and gravely injured a 4th. The incident occurred at the company's plant in Perth Amboy, New Jersey.
Acetylene was produced at the ASCO plant through the chemical reaction of calcium carbide with water in a vessel known as an acetylene generator. The gas then flowed through pipes to cylinders for distribution to customers. Water was fed to the acetylene generator from either the city supply or from outdoor tanks containing recycled water. There was normally enough water pressure to prevent any acetylene gas from flowing backward through the water pipes, where it might find an opening, creating a danger of explosion. The water line was also equipped with a check valve, a safety device intended to prevent the reverse flow of acetylene through the pipes. In normal operation, water flowed through the check valve into the generator. Should the water pressure fall, a plug in the check valve was supposed to block the flow of acetylene. The recycled water was supplied from several large outdoor tanks. The tanks were connected by wooden panels, forming a shed. A drain valve on the recycled water line discharged onto the ground inside the shed. On the night before the incident, this valve was left open to protect the water line from freezing. The next morning, the acetylene generator was started up using the city water supply. The CSB believes that operators later shut off the city supply, opened the valve to the recycled water line, but then, for some reason, delayed switching on the flow of recycled water. Without water pressure, acetylene began to flow backward from the generator. The check valve was the only remaining safeguard to prevent acetylene from reaching the open drain in the shed. But on the day of the accident, the check valve didn't work. The CSB later found that the design of the valve allowed the plug to become misaligned, allowing acetylene to flow back into the water pipe. The gas flowed back through the check valve, through the recycled water line, and out of the open drain valve into the shed. The concentration of acetylene built up to a dangerous level. The CSB believes the acetylene gas most likely ignited when it contacted the hot surface of a propane space heater at the far end of the shed. The result was a violent explosion at 10:36 a.m., which pulverized the shed. The deadly blast wave struck the victims, who were shoveling snow nearby.
The CSB Safety Bulletin outlines a number of good safety practices for managing highly flammable gases, like acetylene. In addition to those safe handling measures, the CSB issued 3 specific recommendations addressed to the companies involved and to OSHA.
Toxic chemicals are gases, liquids, or solids that through their chemical properties can produce injuries or lethal effects on contact with body cells. Oxidizing materials are chemicals that decompose readily under certain conditions to yield oxygen. Dangerous gases are those that can cause lethal or injurious effects and damage to property by their toxic, corrosive, flammable, or explosive physical and chemical properties. Storage of dangerous chemicals should be limited to 1 day's supply, consistent with the safe and efficient operation of the process. The storage should comply with applicable laws and ordinances. An approved storehouse should be provided for the main supply of hazardous materials. Local fire departments should be notified so they'll know what is stored where and can plan for emergencies. The selection of appropriate personal protective equipment for exposure control often requires both an understanding of the limitations of the equipment and the expected exposure parameters as determined by an industrial hygiene evaluation. Engineering controls are considered the preferred method of control, but personal protective equipment plays an important role for health, safety, and rescue. The potential for misuse or misapplication of these devices should be evaluated. Your company is required to have hazard assessments and make determinations which PPE is best to use for each hazard. You will receive more training and information on PPE. The two primary hazards associated with flammable and combustible liquids are explosion and fire. Safe handling and storage of flammable liquids requires the use of approved equipment and practices per OSHA standards. Flashpoint means the minimum temperature at which a liquid gives off enough vapor to form an ignitable mixture. In general, the lower the flash point, the greater the hazard. Flammable liquids have flash points below 100 degrees Fahrenheit and are more dangerous than combustible liquids since they may be ignited at room temperature. Combustible liquids have flash points at or above 100 degrees Fahrenheit. Although combustible liquids have higher flash points than flammable liquids, they can pose serious fire and/or explosion hazards when heated. Some sources of ignition and prevention include static electricity. Static electricity generated when a fluid flows through a pipe or from an opening into a tank. Main hazards are fire and explosion from sparks containing enough energy to ignite flammable vapors. Bonding or grounding of flammable liquid containers is necessary to prevent static electricity from causing a spark.
Late in the evening of October 5, 2006, a fire broke out at a hazardous waste transfer facility in Apex, North Carolina, a suburb of Raleigh. The facility was owned by the Environmental Quality Company, known as EQ. City officials ordered thousands of residents to evacuate their homes. Much of the town of 34,000 was in the area of the evacuation. Some residents were put up in public shelters. Because of shifting winds, the entire Incident Command Center, which involved large numbers of police, fire, and EMS personnel, had to be relocated 5 times. The fire destroyed the EQ hazardous waste transfer facility, and it has not been rebuilt. The Chemical Safety Board investigated and issued a case study identifying several key safety issues. The EQ hazardous waste building had a metal roof and walls and was open on 2 sides. Inside, workers combined small quantities of similar waste materials into larger containers. These containers were stacked in bays along an elevated dock for later shipment to treatment and disposal facilities. In one bay, the company placed returns from retail stores, such as pesticides and paints. Other bays contained flammable and corrosive chemicals and laboratory wastes. One bay was designated for oxidizers. Among these materials was a large box of chemical oxygen generators, which had been removed from aircraft emergency oxygen systems during routine maintenance. Drums of solid chlorine-based pool chemicals were stacked on top of the generators. At 9:38 p.m., a resident driving past the facility called 911 to report a haze with a strong chlorine smell.
Apex 911, location of your emergency.
There is a chlorine leak.
Okay.
You can see a haze through the air, and the chlorine smell is very, very strong right there at the intersection. You can actually see the haze and real strong smell.
Okay.
The Apex Fire Department responded and sent in reconnaissance teams to investigate. The fire started in the oxidizer bay. As it spread, dozens of the aircraft chemical oxygen generators activated, releasing oxygen, accelerating the blaze. The fire spread quickly to the flammable liquid bay, burning through the roof and causing numerous 55-gallon drums of waste to burst, sending fireballs hundreds of feet into the air. As haze and smoke spread from the facility, officials called for residents to leave their homes.
Can you contact fire and ask if we need to start an evacuation back in toward Briarcliff and all that area?
If you could evacuate those people to the parking lot of the community center.
Police and other responders were cautioned to avoid the smoke and haze.
Central Command is advising that you all do not need to be driving in the clouds.
By the next day, about 30 people, including 12 police officers and 1 firefighter, were taken for medical attention at local hospitals. Firefighters determined the best course of action was to let the fire burn itself out. The evacuations ended after 2 days. The CSB found that the unspent aircraft emergency chemical oxygen generators most likely contributed to the growth of the fire. The remnants of many burned-out generators were found in the debris. A fiberboard box of unspent generators had arrived at EQ after they were taken out of airline service at an aircraft maintenance facility. When accidentally activated or exposed to fire, the devices produce substantial amounts of heat and oxygen, which can initiate and accelerate combustion. The National Transportation Safety Board conducted this test, demonstrating how oxygen generators can initiate and accelerate a fire. The test was part of the NTSB investigation of the 1996 ValueJet crash in Florida, which was caused when the devices discharged in the plane's cargo bay. In June 2007, the CSB issued urgent recommendations and a safety advisory, calling for waste oxygen generators to be safely discharged before shipping by any transport mode. At the EQ facility in Apex, the bays were separated by 6-inch-high curbs, designed only to contain spills. The CSB determined that firewalls would likely have contained the initial fire in the oxidizer bay, preventing it from spreading to other bays where flammables were kept. The only fire control equipment at EQ consisted of portable fire extinguishers, which were of no use when the open bay facility was unattended. EPA regulates hazardous waste facilities under the Resource Conservation and Recovery Act. Those rules require what is referred to as fire control equipment on site, but there is no EPA or industry guidance defining such equipment. This allows facilities to operate without automatic fire detection and suppression systems, alarms, and after-hours and weekend monitoring, as was the case with EQ. An automatic fire suppression system might have extinguished the fire at an early stage. The CSB investigation identified 22 other fires and chemical releases from hazardous waste facilities over the past 5 years, including this major fire at another EQ facility in Romulus, Michigan. The CSB concluded that the occurrence of these waste fires indicate there is a serious problem that should be addressed by the National Fire Protection Association, the body that develops the national fire codes. The CSB found that the EQ facility in Apex had not provided written information on the specific types, quantities, and locations of hazardous materials to the fire department or the local emergency planning committee. And when the fire occurred, there were no company personnel immediately available to provide information to the fire department. Fire departments, police, hospitals, and others in the community can better plan for emergencies when they are provided detailed information in advance. Although the EPA does require hazardous waste facilities to provide authorities with information about the materials they store and handle, the regulations do not explicitly state what information must be shared.
Bonding. Bonding physically connects two conductive objects together with a bond wire to eliminate a difference in static charge potential between them. You must provide a bond wire between containers during flammable liquid filling operations, unless a metallic path between them is otherwise present. Grounding. Grounding eliminates a difference in static charge potential between conductive objects and ground. Although bonding will eliminate a difference in potential between objects, it will not eliminate a difference in potential between these objects and earth unless one of the objects is connected to earth with a ground wire. Ventilation. Ventilation always provides adequate ventilation to reduce the potential for ignition of flammable vapors. Storage fundamentals. Storage fundamentals identify incompatible chemicals. Check the material safety data sheet. Isolate and separate incompatible materials. Isolate by storing in another area or room. Degree of isolation depends on quantities, chemical properties, and packaging. Separate by storing in the same area or room, but apart from each other. Storage of flammable and combustible liquids. Storage must not limit the use of exits, stairways, or areas normally used for the safe egress of people in office occupancies. Storage is prohibited except that which is required for maintenance and operation of equipment. Storage must be in closed metal containers inside a storage cabinet or safety cans, or an inside storage room. Safety cans for storage and transfer. Safety cans for storage and transfer. Approved container of not more than 5-gallon capacity. Spring closing lid and spout cover. Safely relieves internal pressure when exposed to fire. Flame arrestor screen. A flame arrestor screen prevents fire flashback into a can's contents. Double wire mesh construction with a large surface area provides rapid dissipation of heat from fire so that vapor temperature inside the can remains below the ignition point. Safe handling fundamentals. Carefully read the manufacturer's label on the flammable liquid container before storing or using it. Practice good housekeeping in flammable liquid storage areas. Clean up spills immediately, then place cleanup rags in a covered metal container. Only use approved metal safety containers or original manufacturer's container to store flammable liquids. Keep the containers closed when not in use and store away from exits or passageways. Use flammable liquids only when there is plenty of ventilation. Keep flammable liquids away from ignition sources such as open flames, sparks, smoking, cutting, welding, and similar processes. Follow the OSHA standards, your company's safety program, and use your good judgment in eliminating the exposure to these potentially harmful chemicals and materials. Safety really does work.